Check it out now, y'all.
nanoHUB-U, online instruction.
All right. So I hope that you are enjoying this set of lectures having to do with settling time. And the basic issue, as I said, was very simple, that if you have some biomolecules in a fluid, then depending on the shape or the geometry of the biosensors, it takes a certain amount of time for the molecules to diffuse to the sensor. And if you have a older style planar sensors, then the diffusion limit goes the square root of dt in terms of the total time required. And as a result, you saw that it takes really a long time in order for the sensor to collect, get the certain specific density of molecules on the sensor surface. A nanowire sensor in that regard was far better because it sort of could collect from all sides, and the geometry of diffusion helped out. And so that was the first week of lectures. I wanted to emphasize the importance of this diffusion limit, often not understood in the nanoscale how important these things are. Now, in this week, in this second week, we are talking about how to beat the diffusion limit. And I just gave you 4 examples, 4 homework problems to work out things on its own. But I want to explain 1 or 2 subtle points associated with this homework. And I hope that if you're having any trouble or if you have any questions, that you will send a note. Because if you get these things correct, understand the details of it, it will be really a very helpful resource as you sort of listen to other lectures on sensitivity and selectivity down the road. So here we go. One of the first problem about beating the diffusion limits, remember there are a couple, right? The first one was Bio-barcode. And the idea was that if you have a set of biomolecules and only a few captured probes, of course, then it is dictated by how long it takes for the biomolecules to arrive at the sensor. These will be immobile sensors. So it takes a long time. You remember that. That's the diffusion limit. So what did you do in order to beat the diffusion limit? Well, what we said, that instead of waiting for the biomolecules to come to me or come to the sensor, rather we'll distribute a lot of biomolecules, a lot of captured probes, so that it can find the biomolecules. So the related example was that here you have 2 policemen and sort of hoping for the robbers to essentially come and give themselves up. Here you throw a lot of policemen so that you can find things, find the culprits relatively quickly. Now, the problem that we had, the first information that was necessary was to see in which limit you are in. Are you in a limit where the number of policemen or number of captured probes is smaller than this formula, or larger than the number of biomolecules? And in that case, it turns out, if you read it, that you will see that we were really in this other end. And in that other end, what happens that the capture time is inversely proportional to the density of the magnetic probes or the capture molecule that you have. Very important to use the correct formula. And also very important to keep the dimensions straight. Make sure that when you calculate the numbers, eventually you get a limits of its time, which is units of a time, which is second. So if you calculate it, I thought that this is relatively short number. And one thing that I often hear when I assign a homework like this is that why is it that in this formula, the number of biomolecules don't matter? Why is it? Because it looks like only thing that matters is how many policemen you have, how many magnetic particles you have. Whether you have 2 biomolecules or 1 biomolecule, it doesn't matter. Why not? The reason is that you can think about the policeman sort of forming a cordon around the biomolecule or around its target. And if you have 2, then they will be captured by the respective group. And so there will be 2 biomolecule receptor conjugate, which will be brought back to the sensor. On the other hand, if you have one will come back. But the time required to capture them really doesn't depend on how many sort of you have. So all of them is sort of boxed off by a certain number of molecules, and that's why this does not have any dependence on biomolecules. The total number of molecules captured is proportional to the number of biomolecules, but the time is not. And that's a very important distinction. I hope when you're working out the homework, you will notice this. The next homework had to do with beating the limit by superhydrophobic surfaces. Now, this is so neat that it is one of my favorites. So what you remember the problem? The problem was that you have a droplet and you have some biomolecules. If you allow the droplet to evaporate, then the biomolecules will be sort of pulled in close to the sensor. And we said that we needed to have a superhydrophobic surface so that the droplet is nicely trapped on the sensor surface and everything will be pulled in, unlike the coughing effect. So I asked you to calculate a formula, and the formula only had the periodicity of the corrugation and the original contact angle. And the surprise was, and that's the reason I wanted to tell you about it, is that there was no surface tension term in the whole equation. That's surprising. I mean, I have the corrugation. Where did all the surface tension go of this original problem? And then I wanted to point out some specific aspect that if you just use the formula blindly, it can give you some unphysical results that you have to be careful about. So I wanted to take this example of Teflon and SU8, two different materials, and show you how or why you should be careful when using this formula. So let me explain those additional details. The math is very simple. I'm sure you can work it out. If not, send me a note. I will certainly help you out here. So you remember the basic idea that if you have a surface with this blue droplet sitting on it, the shape of the droplet depends on the surface tension differential between the liquid and the solid, and the liquid and the gas phase, and the gas phase and the solid itself. And there is a balance, then that gives you the contact angle theta E, which is if you draw a tangent, the angle it forms with respect to the solid surface. Now, if you wanted to sort of pull it in and make it a droplet, right, that is nicely centered, then what we said that what you have to do is to sort of weaken the interaction between the fluid and the solid. They like each other too much. That's why they have been sort of pulled apart. You want to sort of reduce it, and you draw a set of holes, and then that weakens the interaction between the solid and the liquid, pulls things in, and the new angle is theta prime. And the question we asked was that what should the periodicity of these things be in order that you reach a certain theta prime, a certain contact angle? How do you do that? Right. So the equation was relatively simple. You remember that in the original case, the gamma LV cosine theta E, this was the Young's equation. That related, the theta E actually knew about everything. It knew about the solid to vapor surface tension, solid to liquid, and liquid to vapor. So theta E knew everything. And so therefore, remember that once we derived the new relationship between theta prime and phi, which is the periodicity of the corrugation, we also had all this surface tension term. All you had to do now was to replace this blue term with the corresponding red. And if you replace it, then you will see only thing that remains. The theta E knows about all the surface tension, original surface tension, original material, the fluid, the vapor, pairs of materials. It knows them all. And phi is the new variable, which sort of allows you to control the interaction. And therefore, you get a theta star associated with it, right? So although this equation looks simple, this contains all the relevant information. Now, I asked you to Google it, the angle, the theta E angle, And so theta is 69 degrees, about 70 degrees for ACO8. All right. So that means that it is hydrophilic. It likes water. So this is hydrophilic. But if you looked up Teflon, Teflon is sort of difficult to put droplets on because it's sort of hydrophobic. It doesn't like it. It has a phobia for water. And so it's 115 degrees. 90 degrees is vertical. And so 150 degrees. So it will ball up like this with the contact angle being 115 degrees. Now it is hydrophobic, more hydrophobic, I would say. It's not yet super hydrophobic, but more hydrophobic. And if you really wanted to make it super hydrophobic, what would you do? Super hydrophobic means you have to have around 145 degrees. It really balls up that way. What do you have to do? Well, you have to take this material, either Teflon or ACO8, and corrugate them, right? That's the homework problem. And you can do that. And this phi is the corrugation parameter. Remember, so we start here, no corrugation. Phi is 1, no corrugation. And so you can see, what is this number? For the red one, ACO8 starts with 69. And what about this blue? Starts with 115. So we'll start from the right side. By the way, the code that you have, the Octave-U code, that code you can use to calculate it, or you can just use the calculator to calculate this number. It's a simple formula. And so what do you do is that you then start corrugating it. So if you corrugate, so 20% whole, 80% solid. So the angle becomes a little bit, begins to ball up a little bit. And so the angle increases. And same is true for Teflon and ACO8. And continually, it will keep going down. And when you have very little material left, then essentially, they will reach a very large angle, relatively 160, 170 degrees, at relatively small values. Now, the question is, at what point things will become super hydrophobic? Let's say super hydrophobic means 145 degrees, really balled up. You can see that for Teflon with 40%, roughly half corrugation, it can get there. But it requires about 20%. You are left with only 20% of this material in order to get with ACO8. You see, it's mathematically correct. What you just did is mathematically correct. If you say that ACO8 will require about 20% of the solid. But physically, you can clearly see this is wrong. What's wrong? Right? This is something, you can do the homework numerically, that's not a problem. You see, if you have just 20% of this and 80% is, this droplet will not float on top of it. You have just a few points supporting it. So what will happen? The droplet will immediately roll down and fill the gaps. And so therefore, this equation is no longer valid if we are going this low in fill factor. And so therefore, I just wanted to make sure that we put some limit, maybe 40% or 50%. That would be sort of the limit when this equation would be good. If you wanted to go below, there's other equations that we can derive. But here, pushing it this far down will be too much. So just wanted you to remember this. All right. 2.3. 2.3 had to do with beating the diffusion limit by flow. So the idea is that if you have a sensor and you put it in a fluidic chamber, let the water containing the biomolecule run past it. And the hope was that because I'm pushing it, the biomolecule will arrive at the sensor surface quickly. Now you remember the trouble, right? The trouble was that, of course, something that comes quickly also leaves quickly. And so you had to sort of balance between this. And so I asked you to calculate a few things like the Peclet number, which says the degree at which diffusion, drift versus diffusion, how strong it is, the relative strength. And I also asked you to calculate the flux. Good. And you can calculate them all, both. There's a code there to calculate it. the point I wanted to make that this issue about the diameter dependence or radius dependence of the flux. Of course, when the radius becomes small, you will capture less, right? So that's fine. It's proportional to A. But you see, the point is that there is another A sitting in the Peclet number, which is then goes as A squared. And therefore, there is a 1/3. So that means you get another 2/3, A 2/3 from here, and everything becomes almost A 5/3. So it doesn't not only go as directly proportional to A, but it goes faster than that. It reduces faster than that. And that's a big problem. This problem is because it has smaller capture cross-section. This is because things are moving away from the small cross-section fast. These two things really kills the amount of flux that you can capture, especially at small scales. So hopefully for different flow rates in the solution, you have been able to calculate these things. If the flow rate is large, of course, you have a larger probability that you will capture the total flux. And this is off by a factor of 10 when the flow rate is low. That makes sense. So high flow rate is good, no question. If your volumetric flow rate increases, you do catch more. The point I wanted to make is that when you are talking about nanosensors, nanobiosensors, 10 micron versus 1 nanometer, yeah, you do get in some increase, but the reduction is dramatic. So it doesn't really give you as much in terms of net enhancement. And I explain why that is the case. But hopefully by now, once you put all the equations in the formula, this is the numerical result. And if you look at the slope in a log-log plot, by now you have found that the slope is 5/3, A to the power 5/3, as I just explained. So this, just to emphasize that at small length scale, it is really not very helpful to make nanobiosensors small, because and the flow is not very helpful for nanobiosensors. That's the point I wanted to make. All right. The final example had to do with the mean first passage time. And you may remember what the issue was. The issue was that you have a biomolecule. Here is a opening. This is like a cell or something. It's an enclosed volume. And this biomolecule starts walking, randomly diffusing, and then eventually it will get out. The question is, how long does it take? That's the mean first passage time. And we wanted to calculate things in 3D or in 2D and see how long it takes. Now, in order to solve this problem, you have to be a little careful about how you calculate numbers. So let me start with a 1D example. So assume that this thing is 1D, right? And you are injecting molecules at this location X0. And it cannot get out from this door. It's closed. And it can only go out through this green door. So that's where the molecules will come out. And so if you plot the profile, the concentration after a while will be constant. Why? Because there is no flux. So there cannot be any gradient. And so therefore no flux. No current no flux through that door, and there will be a linear profile drop across from the injection point to the exit point. And so if you wanted to calculate the carrier concentration or the biomolecule concentration at any location X, you'd say that this is a straight line because it's a constant flux, and it is given by rho naught, the density. X0. So rho naught divided by X0 gives you the slope. And if you wanted to know how high this ordinate is, you will just multiply with X. In general, you can convince yourself that the way the equation works, that you can write it as CDSS of X0 divided by CDSS at X. Because you see, epsilon naught A over X, epsilon naught A over X0, if you flip it, then you will get this formula. These are planar sensors, so this equation does it well. All right. So then how do you solve this actual problem that I gave you in 2D? The way it works is that you write the CDSs between R0 and exit point. So the molecules have been left here, and so it can walk around and eventually get out through the green point. And so you will have a CDSs of R0. You know it goes as 1 over ln of R0 over A. There's 2 pi epsilon ln of R0 over A. I haven't written that 2 pi over 2 pi epsilon. And then there's CDS R, and that will go as ln of R over A. It's in the denominator, it will flip up. And so as a function of R, it's not really a straight line, but it will have this functional dependence. And so what you have to do is essentially calculate how much charge you have between the green and the red circle. I know the amount of charge at a given location R, let's say in the blue. I have to multiply 2 pi R, that gives me the ring, blue ring, and dr is the thickness of the blue, and I have to integrate between 0 or A to R0, or 0 to R0, right? And then, I'm sorry, this should be A to R0, and once I integrate it, I'll get a formula. So that will be the total amount of quote-unquote biomolecules between R0 and A I have. What about the other piece? So between R0 and B, I will have some more molecules, but those are flat because there's no flux going out of the outer ring. And so I have this flat. And if I have this flat, it will be pi B square minus R square. That will be the total amount of charge I have within this. Think about it. Think about a sort of a constant density ring surrounded it between R0 and B. And so what is the total charge? The total charge would be, oh, by the way, what is the flux? The flux is CDSs multiplied by rho naught. That's the formula that we derived. And CDSs is 2 pi d rho naught ln over R0 A. Remember, if we inject something here between this point and this cylinder, this two concentric cylinder, the flux is given by this. And so if you wanted to calculate the net escape time, you will add these two charges, Q1 and Q2, divide by the current, and that will give you the exact formula, B square over 2D ln of R0 A, and then you have this extra term. So essentially, that was the formula that I asked to derive. The important point is that I wanted to emphasize this equation, rho of R, because this is something, if you have not worked with it before, you might find it a little complicated. The important point is to see that in analogy with one-dimensional case, that a very simple formula tells you what is the concentration at any distance R from the center, as the molecules are sort of diffusing in and getting captured by the center surface. So if you sort of have worked out these couple of problems, you should be in very good shape. But if something is not clear, I hope you'll let me know whether I can explain something a little bit better. Want to emphasize, this is not a straight line, by the way. You can plot it out. It's a log of RA, log of R0 over A. So it will be a curved line. And so it's something that you can plot out. But it's just to give an idea that how the carrier density is not the constant, but rather changing as you move away from A towards R0. Okay. So let me end here with this set of homeworks. Now you'll be preparing for the exam, first exam soon. And the first exam will essentially be a set of problems taken from the quizzes that you have had and a little bit from the homework. But it will be relatively simple. Shouldn't have to worry about it too much. All right. Good luck then for the first exam, and see you for the second set of lectures associated for selectivity and sensitivity. Okay. Thanks.